when you've got 10 gazillion things to do. So I'm about halfway finished. Actually, I'm almost finished getting all the grades into Blackboard for the test. But so some of you have grades, some of you don't. So those are in there. We did have a glitch in WebAssign, and I'm in the process of trying to figure out what students it affected. But the key, I know it's affected at least 2 students. The good news is what the glitch was did not affect your grade in Blackboard, okay? What happened was we apparently had to do a reset in Blackboard, which meant that, and if you followed your Blackboard really, really close last week, all of a sudden you got a whole bunch of weird grades that showed up in this class because I don't normally have WebAssign go directly into Blackboard, but when that happened, the switch occurred and WebAssign dumped into Blackboard all the same duplicate grades. They're now, I haven't messed with them in Blackboard other than hid them from you because they're duplicate columns for the grades that are already in there. And the good news is the other problem that happened that caused that, for some students, it erased all your grades previous. So if you go into Blackboard and you go look at your grades in Blackboard, there are assignments that you may have done that will say you didn't do them, you didn't even look at them, you didn't have it. Good news is I have those grades still in my Blackboard. And this is one of the reasons why I don't have WebAssign just go straight into Blackboard, because I've had this happen to me before. And as many homework assignments as I assign, it's really, really hard to go replicate. So I don't like doing it. So be aware that that's there. We're in the process of working it out, but also be aware that I have everybody's grades. And it seemed to have affected things prior to, it happened, luckily for us, it happened right at a point where I'd already entered everybody's grades because we had a test. And so there's no homework that wasn't already in the system. So, because that was one of the things I couldn't figure out was if WebAssign did all of that, dumped in all those grades, why the grades didn't change, and I know why, because it came in under a category that I don't have figured into the grade calculation. So it was easy to make sure that things didn't happen. But if you go back into Blackboard and you look at your past homework, not anything that was Chapter 6 and on, but your past homework, the grade may have disappeared. So I kind of need to know so that we can kind of chase down the problem. But your grades are already in Blackboard, so it's not going to be a big deal, at least from that perspective. So that's one of the things that's happening there. We are starting momentum, and I told you at the beginning of the semester that there's one topic that I don't understand why you don't understand it, and this is it. Okay? I don't understand why you don't understand it, and this is it. This is one of those things that if everybody has a talent, and their talent can be in a variety of things, and you can always figure out the people's talents because they don't understand why nobody else gets it. Because it comes so easy for them, it comes so straightforward for them. Well, momentum happens to be that one for me. I don't understand why you guys don't get it. Now, I do understand that it's mostly you biological types that don't get it. Because I've had this discussion with my son over and over again, because momentum was one of the ones that he had trouble with, and he's a biological type. So that's one of those pieces there. So please do not get offended if I sound grouchy. Well, I'll be grouchy this week anyway because I got a cold. So that'll be grouchy for that. But I'll be grouchy because I can't figure out how to help you guys really understand it. So rely on your partners, rely on your study groups, because they may be able to explain it in a way that makes it a little bit more sense. I will try, but this is one of those topics that's just a little difficult on my end. So kind of keeping you up to date on that part. So with that, I'm going to switch over to the document camera and we will get started. And we will get going here. Okay, it looks like we've got the document camera. It looks like the document camera's working. My other room the other day, the document camera was upside down and backwards. And it was really fun because the place to flip the camera was not obvious. You know, we turned everything that looked like it could turn, but it was upside down and backwards. It was really weird. So, all right. So we're starting with momentum. And most of you have already done the momentum laboratory in collisions. Momentum is that thing that when you step on the brakes, everybody throws their hands back, try to make sure things don't keep flying forward in the car, right? That's momentum, okay? An object in motion remains in motion except when acted upon by a force. That's why we wear a seatbelt, because we don't want to be the thing that's moving towards the windshield. We really don't want to be a thing that's moving toward the windshield. Those of you who are car enthusiasts, I think it was the last issue of Car and Driver that looked at the new safety features in the cars and talked about the wrecks that people actually walked away from, and showed the cars that they walked away from. In fact, it was one of the Car and Driver test drivers that was in a wreck that they were going 120 miles an hour, screamed off the edge of an Alp, I believe, went into the ravine. The car tumbled 3-4 times. It was an exotic car that they totaled on the test drive. But both of them walked away with scrapes and bruises once they could get out of the car. So that's, I mean, so the shell of your car is engineered so that you can get up and walk away, and most of the deaths occur because you were not wearing a seatbelt. Now the seatbelt will and has created, injuries, but I don't know about you guys, but I'd much rather have cracked ribs due to my seatbelt restraining me in my device than being thrown through the glass window or the front windshield and not surviving. So the seatbelt is there to keep you inside the cage that is the safety cage of the car. So it is a big deal. But that was last month's issue of Car and Driver. We're reading Car and Driver these days instead of Road and Track. So just kind of going back and forth. There's a great article about it. But momentum is that thing that's, an object in motion remains in motion except acted upon by another force. Now we've already talked about conservation of energy. And there's conservation of mass. And we will have conservation of momentum. And it's both linear and angular. So even though we're not going to start with angular here, we will have conservation of angular momentum as well. This is the ice skater problem, okay? That's why the ice skater, when the ice skater goes into a spin, if the ice skater is extended and stretched out, that the ice skater is going to spin slower than if the ice skater is in a tight spin. And I will actually post a bunch of National Science Foundation videos that relate to momentum. And I will post some other videos that relate to momentum. So some of you gamers out there that, EA Sports talks about their momentum and their collision and their ragdoll physics, that they can actually do something on the order of 500 calculations per second in order to get realistic collisions, particularly in EA Sports hockey. Because when because if you watch hockey, we will actually use a lot of hockey examples because hockey's easy to talk about momentum in. And they will actually show the ragdoll physics, and I will post all of those videos because they're pretty cool when we're looking at momentum. So, as I told you guys early on, I don't like to teach force without starting to talk about momentum because Newton really looked at this, and we use P. Don't ask me why. I have no idea why we use P to mean momentum. And 9 times out of 10, I only use it to do the initial discussion. I very, very rarely use it anywhere else. But P is the symbol for momentum. Momentum does have a vector quantity associated with it. And basically what this is saying is if I have a soccer ball and I have my foot kicking the soccer ball, I apply what we call an impulse. And that kick will send off the soccer ball off to some place. And we end up with what we call a change in momentum. So we end up with that change in momentum. I'm going to see if I can scroll out a little bit. And that impulse is going to be important. And in fact, the impulse, and it's what's happening with the impulse that's going to save you a lot of times in a car crash. Okay? It's what's going to save you. It's what saves IndyCar drivers. It's what saves NASCAR drivers. It's what saves a variety of things, because we were actually wanting to look at that impulse. Because if I'm getting a change in momentum and I'm going from 100 miles an hour to 0, the longer it takes me to do that, the less force that gets applied. Because I've got a change in time that's directly proportional to my change in momentum. So I will also post some NASCAR videos talking about safer barriers, because those safer barriers extend the length of the crash. So instead of just hitting the brick wall instantaneously, you get some give, and that give is going to allow you to slow down that crash, which reduces the amounts of the force. So if I take a crash and the crash lasts 0.1 seconds, if I've done something to make the crash last 0.2 seconds, the forces on your person are reduced in half. So it makes a huge, huge difference in terms of time. That's why those barrels are stacked up in front of the concrete pylons for bridges. That's why your guide rails are there, is to slow you down over a course of time, and that's why you have crush panels in your car. It's all about extending the time to have that crash occur, because the momentum change is going to be the same. You're going from 60 miles an hour to 0. The only thing that we can control is how fast you do it. That's the only thing that we can control. If we do it in a very short time, we're going to have a big problem. And that's going to result in the forces that ultimately can harm or hurt or kill someone. So that makes it's a big difference in that terms of time. So impulse is directly related into momentum. And we've actually talked about it. Remember that the common version of Newton's second law is this right here. This is actually how Newton wrote it, which is actually better. But if we look at momentum, momentum is defined as mass times velocity. And it does have direction, so we're bringing direction back. We do have to keep track of direction. And this is one of those chapters where no matter what you say, it would be nice if I could just know the equation that I can plug in and then I can work it. Unfortunately, in momentum problems, there's never the equation that you can plug it in, because you have to create your equation for each individual situation. You have to actually create your equations. And it's going to come from that the momentum before equals the momentum after. Always going to come from the momentum before is equal to the momentum after. So, do I have hockey fans? Anybody? I got one hockey fan back here. Do I have any other hockey fans? No hockey fans. Oh, bummer. Do you know the Red Wings? So what hockey team do you follow?
Whatever's on.
Whatever's on? Okay. Do you know about the Red Wings? I think it's the Red Wings. Has a weird habit. The fans throw octopi onto the ice. I'm hoping they're rubber octopi. By the way, October actually has celiac, what are octopi? Octopi and squids and encephalopods, thank you. And there's National Encephalopod Day, we had it this month. Just so you know, okay? So octopi are really interesting critters. They're very, very smart. I don't know why, and I don't know exactly how the tradition started that the Red Wings will throw that on. Does anybody know why hockey is in 3 periods? It's the only sport that's broken up into 3 periods. Didn't used to be. Actually usually has 2 halves. It's all about the ice. It's ice maintenance. To allow for ice maintenance. That's why hockey's in 3 periods. But hockey's all about momentum and impact. Impact, impulse, and momentum. Because if you think about it, if you watch hockey, right? If we watch hockey, we can watch the guys dribble the puck. Okay, that's what it's still called, dribbling. You can dribble the puck. And the puck has got, and they can just lightly tap it, and the puck will just go a little bit back and forth, back and forth, back and forth. Then they hit it really hard, and it can zing, and it becomes a rocket, and becomes a ball bearing that's bouncing around the rink. And it's a hard rubber vulcanized plastic is the puck. I do have the amounts in my notes because I use hockey puck examples a lot, so I know what the actual NHL official hockey puck is. And it's solid ice, and if it's coming at you and it hits you, it's going to be, that's why you wear pads, right? That's why we wear pads, and that's why goalies don't have any teeth, right? That's why we do it. So hockey gives us lots of good examples for impact, impulse, and momentum, and it gets in there. But you can all think about it. Those baseball players, because I know I got a lot of baseball players in here, and those softball players, you know that if somebody is hitting a screaming ball and it hits you, it hurts. But if that ball still comes at you and it's coming at a slower velocity, it doesn't hurt quite so much, right? It doesn't hurt quite so much. And if I can hit it with my glove, I can deflect it a little bit so it doesn't hurt quite so much. But even if I have something that doesn't have a whole lot of mass, if it has a whole lot of velocity, it's still going to hurt. Think of a .22 caliber rifle bullet. That doesn't have a whole lot of mass, right? .22 caliber, the lead part of the .22 caliber bullet does not have a whole lot of mass. It has a whole heck of a lot of velocity though, and that's what kills you. The fall doesn't kill you, it's the impact at the end, right? That's essentially what it is, because we got a change in momentum. We have a change in momentum. So let's go back here. So we got force is equal to mass times acceleration. This is Newton's second law. But if I write it out this way, I've got my force times my change in time is equal to my change in momentum. And if we looked at it, because we talked about the fact that usually the reason I don't have to worry about this is that the thing does not have a change in mass, because really what this says is that this times my change in mass plus mass times my change in velocity, that's what that actually breaks out to. We don't usually have a change in mass, so I don't have to worry about it. So if I take my change in time, I get mass divided by a change in velocity over a change in time. That we know is acceleration, and that gives us Newton's second law. Okay, that's what gives us Newton's second law. So we get impulse and change in momentum. Okay, that's as far out as it's going to go. I can get it all on one page. That's good. But we use that change in momentum, and we're familiar with it because we've all played with momentum. We use it to our advantage, and we use it to our disadvantage in other cases, but we use it to our advantage. One thing that we do know is if I have a change in momentum, for example, we've all seen this toy, right? This is called Newton's cradle. And if I take this one and I put it back and I let it drop, we know that this one, it comes out the other end. And the thing that we know about, the thing that's unusual about it is it seems like it's counterintuitive that the rest of these don't go off as well. But what's happening is that we have little incremental changes in time for each one of these. And we have a series of collisions, and it's not until we get to this one that doesn't have anything to collide into that it's just going to actually swing off. We also have some interesting conservation of energy problems associated with Newton's cradle, which makes it really kind of nice because we can take 2 of these back and we get 2 of these off. And again, it's because of these little instantaneous pieces of time that we're not, that we don't get, that we have a whole bunch of things go off. So if we do this intuitively, and we've played marbles before, almost everybody's played marbles, even if they don't think they've played marbles. We take a marble, and we have a marble sitting here, just sitting there with a velocity equal to 0. And this marble comes in, and it's got some velocity. And it's going to go, so this is the before side. And if everything works perfectly, our first marble ends up sitting still, and this marble goes off. And we know that if these 2 things have the same mass, this marble goes off with the velocity that this marble started with. And this is the after side. So this comes in, this goes off. Now, in real life, it doesn't quite work that way. Marbles work pretty well that way. Billiard balls work pretty well that way. Pool balls work pretty well that way. But not everything does. In real life, what happens, so let's take our pool cue, our cue ball and another pool ball. In real life, what happens is the cue is going to be moving at a much, much less velocity than it had initially. And this one is going to be moving off close to the original velocity of the cue ball. This is just going to dribble a little bit, and this one's going to move off with the velocity. So if this one has an initial velocity of 0, and this one has my velocity of the cue ball, we know that this one kind of peters out just a little bit. Peters out just a little bit. Now this is linear momentum. So we're going to end up with linear momentum. A couple other things that we know because we've done it. If I take a tennis ball or a racquetball or a basketball and I hit the ball at an angle, it's going to bounce off at another angle, and we end up having that these 2 angles are the same. And one of the reasons that we're going to get this law of reflection, that's what it is, it's a law of reflection, is I've got to have a change in momentum, but the wall's not going to go anywhere because the mass of the wall is so much bigger than the mass of the ball. And I'm going to get the mass of the wall so much bigger than the mass of the ball, we're actually going to see it bounce off. So we intuitively have been playing with momentum a long time. We know a couple of other things. Now these kinds of collisions, the collisions with ball bearings, the collisions with pool balls, where they come off, and you guys actually saw it in lab, and I'm going to have changes here. We called this an elastic collision. Okay? And in an elastic collision, things don't stick together, things don't have deformation, things don't have anything that's going off there, and my before and my after are nice and clean. Now, there is no such thing as a truly elastic collision unless I'm in space. But billiard balls, ball bearings, marbles, hockey pucks, pretty darn close. Air hockey pucks, pretty darn close. Very, very close. Then we have what we call a totally inelastic collision. Okay? An inelastic collision is one, so let's take a target here, and I've got my little bullet hitting my target, and now that's the before part. And the after part is that my bullet is now embedded in my target. That is a perfectly inelastic collision in that the two objects are actually going to totally join together. Now there are collisions that are in various stages of elastic to inelastic collisions. The ones where the bullet goes through the target, that's an example of an inelastic collision. But I still have, it's certainly not an elastic collision. It still is an inelastic collision, but I have some other things that I have to worry about. The car and the train on the tracks is an inelastic collision. It's not a totally inelastic collision because what happens to the car if the train hits it? Well, it's going to be deformed, but I got parts flying everywhere.
Yeah.
I got parts flying everywhere. If my perfectly inelastic collision is that they become part of each other, what happens to my car is that it's going to explode off into a gazillion pieces and it's going to go flying.
Yeah. That's kind of messy.
And it's very messy. It's very messy. But I have various stages. Now, we will show it and we will play with it, but the definition of an elastic collision, there's an actual definition of a perfectly elastic collision, is that this is a special case. In all collisions, no matter what we do, all collisions, momentum is conserved. In all collisions, energy is conserved. Okay? We have conservation of energy, we have conservation of momentum. This tricky thing about elastic collisions, it's a special case when kinetic energy is conserved. Okay? Doesn't matter, I can have inelastic collisions, energy is still going to be conserved. Because in an inelastic collision, when the train hits the car, I hear a boom. Sound is a form of energy. If I'm lucky, I might see sparks. So that's light. So that's a form of energy. I got parts flying in a gazillion places. I've got heat buildup due to friction. I've got lots of other places the energy can go. So I'm still conserving energy. Whether or not I can capture all of it is a different story. But in a perfectly elastic collision, I get this weird case when kinetic energy is conserved. Now remember, kinetic energy is equal to 1/2 mv squared. So if you think about that for a second, it's a little interesting that we get this weird case, and that's why elastic collisions are a special case. They're a totally special case because they are going to get kinetic energy is conserved. So let's play with a couple of these. Let's play with a couple of these. Oh, let me see. Let's do a basketball player problem. All right. So we've got a person here. And we all know my people are, they're all stick people. They're totally stick people. And our person is going to have a mass of 65 kilograms. And our person is going to, so person has a mass of 65 kilograms and is going to jump up from a standstill with a velocity of 1.8 meters per second. Okay, jump up with a velocity of 1.8 meters per second. Now, momentum has weird units, by the way. Momentum is mass times velocity. It has kilograms, meters per second. And the other interesting thing is, for whatever bizarre reason, we didn't give it a name. We gave everything else a name. We just don't give momentum a name for its units. We just carry them through. But I've got my momentum. What we're going to want to do is we want to find the impulse. Let's see if I can't spell today. We want to that the impulse that the player had to provide in order to have this jump happen. We want to figure out the force on the floor by the player. Okay, force on the floor by the player both before the jump and during the jump if the jump takes 0.45 seconds. All right? So if I'm going to do my force diagram, I've got mg here, I've got my normal force. So we know what the force on the floor is, right? We know what the force on the floor is. It's going to be mass times gravity. That's going to be my 65 times my 9.8. And this is going to give me kilograms, meters per second squared, which is going to give me newtons. And if I do that, I get 637 newtons. Now, depending on how I write the question, the player is providing a force to the floor of 637 newtons. The floor is providing a force on the player in equal but opposite forces of 637 newtons. So we're okay there, because we've been doing that for a while. If we want to do impulse, and remember there's nothing that says you have to do the questions in order. They're helpful, but not necessary. My impulse is going to equal my change in momentum, and that becomes the momentum after minus the momentum before. Mass is going to be the same, so I can just look at my change in velocity in this case. So my mass is going to be my 65 kilograms. My final velocity is 1.8 meters per second. My initial velocity was 0 meters per second. And so the impulse was 117 kilograms meters per second. Okay. So now if I want to look at the force that the floor, the force that was being applied during the jump, okay, that impulse, force is my change, this is my impulse, this is my change in momentum. We already figured out the change in momentum was 117 kilograms meters per second. Okay, and then my force is going to equal my change in momentum divided by my change in time, which gives me 117 kilograms meters per second divided by my 0.40 seconds, 450 seconds, and this gives me 260 newtons that was applied during the jump. So let's look at that NASCAR example. So I got my NASCAR guy that's going to get forced into the wall, right? And if he's moving at 100, let's see, so 27 is 60 miles an hour, so he's moving, let's go ahead and do 60 meters per second. This is going to be around 120 miles per hour. Okay, a little faster. And if we're gonna hit the wall, and a NASCAR car's probably on the order of 3,500 kilograms, I may be a little light. But about 3,500 kilograms going at 60 miles an hour. If it hits the brick wall and the collision takes the change in time going from 60 meters per second to 0 meters per second is 0.3 seconds. We can calculate the force on the car. So the force is going to equal my change in momentum divided by time. So that's going to be my 3,500 kilograms divided by 0.3 seconds. And I'm going from 60 meters per second to 0. Now, these are backwards because it's going to be a negative force. This is a stopping force. But we're looking at magnitude. So if I do my 3,500 divided by 0.3 times 60, gives me 7 newtons.
Oh, yeah, I was gonna say, why not?
700,000 newtons. Now, if I can extend that time to 0.5 seconds, it's only 4,200. So that's why those collision barriers, those collapsible barriers are so important. Those collapsible barriers are very, very important. Now, this was the force during the jump. This is the force just standing there. So if I'm looking at the total force on the floor, I have to sum up my forces. So I'm going to get my 637 plus my 260
I can't see.
plus my 260. When I add that together, I'm going to get 897, which would be the total force on the floor during the jump. Let's look at some, so you have a few impulse impact problems. Now let's look at good old cart problems or good old, so if I have an object and we're going to say it has a mass of 10 kilograms. And we've got another object and it's got a mass of 20 kilograms. This is the before situation. And we're going to start out with an initial velocity of 10 meters per second. This one's going to have an initial velocity of 0. We want to know what happens if this mass now has a velocity of 0 and this mass is going off. We want to know the velocity that it's going off at. Okay, so this is the after situation. So we got a before and an after. So the way I do these problems is I start out here at the momentum before, has to equal the momentum after. So I'm going to do the mass 1, velocity 1, initial. Subscripts are really going to help you out when you work these things. They're totally going to help you out. Mass 2, velocity 2, initial is equal to mass 1, velocity 1 after, plus mass 2, velocity 2 after. Well, we know the initial velocity here is 0. We know the final velocity there is 0. So I can get rid of those terms. So I get m1 velocity 1 initial is going to equal m2 velocity 2 after. I get m1 velocity 1 initial divided by m2 equals the velocity after. And so this is going to be plugging in numbers. 10 times 10 divided by 20. And if I look at my units, I get kilograms, meters per second divided by kilograms. The units are going to work out nicely. And I don't trust in my head multiplication today, or division. This says it's going to travel off at 5 meters per second. And most of us probably knew that already because we went, well, this is going 10 meters per second. This is twice as heavy, or has twice as much mass. It should be going off at half the velocity. So you can check yourself on this because you've played with this. You've done it. You've seen it. But again, we say that this doesn't usually happen, right? That part doesn't usually happen. So that, what usually happens is this doesn't go completely to 0. This is now traveling at a velocity of 1 meter per second. So let's do the thing again and see how fast this one's going to go off. If this one is going at 1 meter per second, well, the momentum before has got to equal the momentum after. So I get mass 1, velocity 1 initial plus mass 2, velocity 2 initial is equal to mass 1, velocity 1 after plus mass 2, velocity 2 after. Well, now we know that this is the only one that can go to 0. But now I have mass 1, velocity 1 initial is equal to mass 1, velocity 1 after plus mass 2, velocity 2 after. So I get mass 1, velocity 1 minus mass 1, velocity 1 after divided by mass 2 gives me my velocity 2 after. So now we can plug in numbers, right? So I get 10 and I get 10 minus 1 divided by my 20. This gives me 4.5 for the velocity 2 after. But if I'm dealing with bumper cars, let's say this time, this is a 20, let's say this time, now this one is assuming these are both moving off in that direction. So I'm going to mix it up. We're not going to go off in that direction. We're going to say that this one has an initial velocity of 3 meters per second that way. And we're going to have a head-on collision. Okay? Now, I'm going to need a little bit of information here. We need a little bit of information. And we're going to say that after this collision, these two things are going to stick together. Because that's usually what happens when we have a head-on collision, right? So these two things aren't going to go off separately. They're actually going to stick together this time. And we want to know, because they're going to actually be like this, we want to know the velocity of that mass going back and forth. We don't know direction at this point. So we're going to figure that out. So mass 1, velocity 1 before is going to be mass 2, velocity 2 before is going to equal mass 1, velocity after plus mass 2, velocity after. These two are the same because we're sticking them together. So we can actually rewrite this as mass 1 plus mass 2, the velocity after. This is a truly inelastic collision. But I also now have to account for the direction. What I showed you before doesn't account for direction. This now has to account for direction. So I'm going to call this direction negative. So I'm going to have my 10 kilograms times my 10 meters per second. So I'm in kilograms meters per second. Plus my 20 kilograms minus my 3. And I'm still in kilograms meters per second. Is going to equal my 30 kilograms times my velocity after. So I'm going to have 100 minus 60 divided by 30 is going to equal my velocity after, which is going to give me 40 divided by 30. And it's going to be positive, so I know my velocity is going in that direction after the collision. And we'll be moving off at 1.33 meters per second. Now, if this thing were moving at even 5 meters per second, well, if that's a minus 5, that becomes 100, and they're going to come to a dead stop. And they're going to come to a dead stop. Now, of course, this is all discounting friction. Right now, we're in a frictionless system. Because I can lose energy associated with friction, but we're going to have different types of collisions. So dealing with our situations becomes really important. Now we can complicate things, right? Totally complicate things. All right, so I've got a 0.3 kilogram bullet. We do not know its velocity. We have no idea what its velocity is. It's going to hit a target, and my target is going to have a mass of, we're going to give it as a 5 kilogram mass. And we're going to make the assumption that after the collision, the bullet is into my target here. Okay? Bullets into my target. This has an initial velocity of 0. But we're going to allow this target, we're going to put this target on a swing, and we're going to allow it to swing up to a height. This is called the ballistic pendulum. And the height that it's going to move up is 1.2 meters. We want to know the initial velocity of the bullet. So we know that the momentum before has to equal the momentum after. So on this side, we have the mass of the bullet, velocity of the bullet, plus the mass of the target, velocity of the target is equal to the mass of the bullet plus the mass of the target times the velocity of the target after. Well, we know that's 0. So I got mass of the bullet, velocity of the bullet is equal to the mass of the bullet plus the velocity of the mass of the target times the velocity of the target. We don't know this one, and we don't know this one. But I have information to figure this one out. Because on this side, I can use conservation of energy. We know the energy at the top has to equal the energy at the bottom. We know the energy at the top is just mgh, right? Now, just after the collision, the pendulum is going to have kinetic energy of mv, velocity of the target. So I can get rid of this part because I don't care about the mass. I get 2gh is equal to the velocity squared. I get the square root of 2gh is equal to v. So I get the square root of 2 times 9.8 times 1.2.
Is it minus 1.2?
No, times.
Okay.
Gives me 4.84 meters per second. Now I can plug that just back in here. So I get mass of the bullet, velocity of the bullet is equal to the mass of the bullet plus mass of the target times the velocity of the target. So the velocity of the bullet is equal to mass of the bullet plus mass of the target, mass of the bullet, velocity of the target. So this is, we said we had 5, so this is 5.3 kilograms. Divide by 0.3 kilograms times 4.84 meters per second. Sorry, I got a key there.
I see it 5.3.
This is 5 kilograms, this is
Oh.
0.3 kilograms. I added them together. This says it's 85.7 meters per second. I'm going to do the train problem. We're going to smash a poor Volkswagen Beetle. And we'll show you why the train doesn't even know it hit something. So when the engineer says, I didn't know I hit anything, you can figure out why. So I have my train here. I got a cow catcher. So my Dr. Seussian train, my little Volkswagen Beetle sitting on the track. So its initial velocity is equal to 0. And my train, of course, has got, and since this one is this way, oh, everybody, so here's fun fact. What should be in the hopper here if I have that kind of a cone on my train?
Oh.
No, if I have that kind of cone on my train, it should be wood. Because that's a spark arrestor. Just so you know, because if you ever look at the Golden Spike, One train has this kind of stack on it, the other train has this kind of stack on it, that kind of stack is the coal train, this kind of stack is the wood train. Even though I drew the coal in the coal car. But basically, that is a spark arrestor. So another fun fact, just another fun trivia fact that you have for trivia night. So we're gonna say our train here, we're gonna give our train a couple of cars afterwards, and we're gonna go ahead and say it has 100,000 kilograms, which is not unreasonable for a train. My Volkswagen Beetle is probably about 2,500 kilograms. We're going to be really nice, and I put a cow catcher on the front so that we're not smashing the poor Volkswagen Beetle, but the Beetle is going to become part of the train. It's going to scoop up onto the cow catcher. Okay, that's how we're going to do this problem. Our train, because it's moving through the city, is slowed down, and we're going to only have it moving at 20 meters per second. We want to know how fast it's going after the poor Volkswagen Beetle gets attached to the train. So the momentum before is going to be the mass of the train, the velocity of the train, plus the mass of the car, the velocity of the car, and it's going to equal, because we're going to put the car on the train afterwards, so I get the mass of the car and the mass of the train and the velocity after. This starts out at 0. So I'm looking for the velocity after. I'm going to get the mass of the train, velocity of the train divided by the mass of the train plus the mass of the car is equal to velocity after. So now I've got my 100,000 kilograms times my 20 meters per second divided by my 102, 500 grams or kilograms. 0.976 times my 20 meters per second gives me 19.5 meters per second. So if it's a pedestrian or a person on the train, the conductor's not even going to know anything happened. They won't have a clue that they've hit something. Because that's not a very heavy train. That train right there is not, that chain right there is nothing. A diesel locomotive by itself, one diesel locomotive by itself is on the order of 50,000 kilograms. So that's 2 diesel locomotives. So if you've got a train that's got 2 diesel locomotives plus all the cars that it's pulling, it's not even going to know it hit a Volkswagen. The operator of the train is not going to have a clue that it hit anything. Unless they get lucky and happen to see it.
It didn't slow it down that much, did it?
Nope, doesn't. That's why you're going to lose with the semi.
Don't play chicken.
You're going to lose with the semi. You're going to lose if you're in a small smart car versus an SUV. You're going to lose. You're going to lose. My favorite was Big A underneath the basket, and the poor little guy from somewhere last year just went bing right off of him. You kind of go, yeah, he ran into a wall, you know. That's why those big tackles, you know, how those running backs can bounce into them, I don't know, you know, because it's all the momentum. See, football has lots of momentum in it. I'm going to leave it there, let this gel a little bit, because I can go on to do more. We will continue to do more, but I want you guys to have the opportunity to kind of play with it and think through it a little bit.